And then yeah, it was the class was run in almost the same manner, just as a flipped class where you just watch the CS231N and then post your questions, and I'll explain yeah, on these questions, and also yeah, and so and yeah, maybe good thing about it is that it was taught in Korean, so yeah, so it is actually in Korean. So whether you like it or not, you can actually utilize this resource as well. Does anyone need more time? Okay, I'll probably close the quiz maybe in the next 3 or 4 minutes. Yeah, before starting the class, any questions? And also, regarding the next week's class, we will cancel our class. Okay, so I thought of preparing for some programming kind of sessions, but I think it's too early. Yeah, but instead, I will give you some video lecture link so that you can kind of self-study. So you are already doing the self-study for the CS231N. I understand that, and also I want you to study some of the lecture videos that I posted, okay, which is like additional or helpful kind of material that can then they can help you understand what we are currently studying in a better manner. Okay, and okay, so again, this is slido.com, and then the access code is the same, KUDL, and then you can post questions over here, or you can just feel free to raise your hand and then ask the question. Okay. Yeah, again, the term project is at a team level, so you can form the team up to maybe 3 people, including yourself. Okay. Although you can of course do the term project individually by yourself. Okay. And quiz, mostly it's a really simple answer or multiple choices where you don't have much opportunities to just enter Korean. It's not like describing your answers in detail, right? As you can see from the first quiz that you just took, it's just composed of quite simple questions. Okay. Yeah. I don't know who is Andrew, but yeah. Technically, it's different, but practically, I will not check the attendance quite often. Maybe just a handful number of checking the attendance. So you can think of these quiz are working as kind of attendance check. But as I mentioned, don't do cheating on just taking the quiz. If you are absent or you don't attend the class, and then just give the quiz up. Okay. Otherwise, if you do the cheating, and then you might get really danger in getting F immediately. Okay. Okay, before addressing these questions, let me just try to do this kind of example again. I don't know why it didn't work, but it seemed to work quite well. When I got back and then tried it. And so, see, we can immediately see it is forming the decision boundaries quite properly, right? And also, so there is no regularization, but in the case of an activation, it should be selected as it should be sigmoid. Okay, so in that case, we are using 4 input variable and then linearly combining them and then passing it to the logistic function or sigmoid function. So that's what this means. Okay, so in this case, so yeah, in most of the cases, yeah, it's just performing really immediately. Okay, and then let me just refresh this like this. Okay, so what are these? What are these initial kind of figure? Okay, so these are the decision boundary and the prediction scores based on the current random initialization, right? And then let's think of the form of some kind of random initialization. So if you remember the class last time, it is just composed of a linear combination of those 4: ax1, bx2, and cx1 squared, and dx2 squared plus e, which is our bias term, right? So that is our decision boundary, making it equal to 0, right? So by just changing some of these coefficients, yeah, we can actually we can represent a quite rich kind of set of curves, right? So by just setting the coefficient for these, we can have a linear decision boundary, of course, right? And also by setting those coefficients as 1 and 1, okay, 1 and 1. In that case, what would the decision boundary be? It's a circle, right? What if we have maybe different positive numbers but different numbers, maybe 2 and 3 as a linear combination coefficient? In that case, it's an ellipse, right? Ellipse. Well, what about having maybe negative 2 and positive 3? Right. So that's what is the name of that curve? 뭐라고 그러죠? 한글로는 쌍곡선? 이라고 하고 이게 뭐더라? 영어로? 하이퍼볼릭 뭐였죠? Okay, so yeah, this kind of thing, right? Yeah, and also, what if we have one of them as 0? So only one of these second order term being non-zero, and the other one is 0. In that case, 또 까먹었는데 포물선? 포물선. 네. 포물선 이렇게 생긴 거 알죠? 네? Quadratic curve? Is it? I thought all these cases are called belongs to the category of a quadratic curve because they are just a quadratic function.
Oh, yeah, you're right.
Yeah, not sure. Yeah. Okay, so that way, by adding just simply the 2 additional kind of feature augmentation of x1 squared, x2 squared, we can have much richer set of decision boundaries that we can represent by our model. Okay. Okay, and then it's rarely happened, but I found that in some of these initialization, like this. Okay, so in this case, it's just a plane or currently being trained, but it's not properly learning the decision boundary, right? What's the reason for that? I mean, what's the phenomena related to that? So what caused that to fail to learn the decision boundary properly? So that is because we started with the bad random initialization, and thus that's like we got trapped into the bad local minima. Okay, right? So you guys know kind of convex or non-convex functions and things like that. Okay. And then one more thing here. What if we set it as a linear? What if we set it as a linear? So in this case, although it looks like being properly trained, right? So it doesn't seem to matter whether we have a sigmoid or a linear. Oops. Okay, so in this case, after we aggregate or combine them as a linear combination, okay, and then in terms of this nonlinear unit, in the case of linear as a nonlinear unit or this activation function, and then it means we don't actually apply any additional nonlinear functions or nonlinear units. So the output should be just a linear, linear combination as just the final output. Okay. So in this case, what will be the problem? I mean, although it doesn't seem to have any problems here, but in this case, it's generally not. These are not recommended. It's not proper kind of application of our machine learning model. And why? Can anyone give a reason? So what's the issue here?
You have to modify input features.
Input features?
Polynomial something other than x1, x2. In this case, we use x1 square and x2 square, so we use the activation function, linear activation function, but we can find weight of x1 square and x2 square, so that we can circular boundaries.
Right. Yeah. So basically, when just looking at the linear combination equation or form, linear combination form, yeah, we have no problem of forming this circular decision boundaries and so on. But that nonlinear, I mean, the activation unit is just applied to the final output of this linear combination, right? So it's a related, yeah. So my point that I'm trying to make is related to like the task setting or problem setting here. So it is basically a classification problem, not a regression problem, right? So all these all the possible class labels or output ground truth values corresponding to our output is either 0 or 1, right? So if we just use a linear combination as our final output, okay, and in that case, in general, our y values will be ranging from negative infinity to positive infinity, right? And so why do we? So I'm talking about like the story where we move from a linear regression to logistic regression. What was the problem? So if you remember, I mean, if you watched or studied the Andrew Young's linear machine learning course, and then let's see. Where is a logistic regression? Yeah, it's a little bit dirty, but so yeah, if you watch it, Andrew Young's machine learning course, you might remember this example. But yeah, so this one is the example where we have only one input feature, and then including the bias, our linear model will be just y equals ax equals b, y equals ax plus b, and we will form the line, and then we have to fit these corresponding y values into the given ground truth y value, right? But in these cases, they are either all zeros or ones, right? So in this case, like the decision boundaries are formed around here. So if it is less than this value or less than this value, then it will be classified as a negative. And if it is larger than that, and then that corresponds to the decision boundaries over here to the right, and then right. So if we have one example over here, which is really clearly positive one, and then this linear decision boundaries, I mean linear model should be like it should be like this, so that we can fit between this value, which still have the ground truth y value as 1, but in the case of linear output, I mean linear combination output, it can go to easily like positive infinity, right? So in that case, our model is saying this data item is really, really positive, but yeah, that positive value around over here, that should be like suppressed, right? So that way we introduce sigmoid function, right, or logistic function, right? So so in that case, the decision boundaries may not be properly learned. So yeah, in this case, the same problem will exist, right? So yeah, basically, by applying logistic function, we have to set the bound of our output from the linear combination as between 0 and 1, right? So it's related to like logistic regression. So if you are not understanding what I'm currently talking about, then please review this linear regression and logistic regression more carefully. Okay. Any questions so far? Okay. There's another Jaguar tree here. I'll send an announcement later, maybe in a week or two. But roughly, you can form the team maybe until this month. Okay. Okay. So let me briefly go through our slides. Yeah, first of all, we mainly learned about different loss function in this chapter 2 and 3, right? And let me just point out one really global rule that you have to keep in mind, although it's quite simple. The loss, can the loss be negative? So is it possible that your loss value at some point or at any point be negative? So it is not, right? So when talking about the loss, right? So it is always greater than or equal to 0, right? So if you see in any cases while doing the programming or when doing some exercise or solving some problems, if you see negative loss value, and then it means something is wrong. Okay, whether you have some bug in your program or in your calculation. Okay, and then. Let me just discuss first about this k-nearest neighbor classification because that comes first, right? Okay, so let's see. So have you played with the k-nearest neighbor demo in this website? Let's see. Not this one. So I think you guys all know how the k-nearest neighbor classifier works, right? And then here a few points that I want to make here is, so this is the decision boundary when the number of the k value as 1, and then 2 and 3 and 4 and so on. Let me just So I'm just gradually increasing the k value. So what is the white region here? For example, like this. What's the white region? Does anyone know? Can anyone guess? 네? 바운더리? 바운더리가 이렇게 두꺼워요? 네? No majority. Yeah, right. Yeah, right. So it's the case of having tie scores, right? So you know how k nearest neighbor classifier works, but that wide regions are corresponding to having the two or more classes having the majority scores or majority vote, right? Okay. So if we had maybe k as 5, and then what's the region for this? And then the possible tie scores are like the two of the classes have gotten or received the 2 votes among 5, right? So it's like 2 and 2 and 1, right? So those regions are corresponding to that. And also related to that, when typically using k nearest neighbor classifier, so let me just show the example. So between 2 and 3, which one has a wider or larger wide regions? It's basically, 2 has larger wide regions, right? So if we use even numbers as a k, and then the even number, initially the even number will have a higher chance of getting multiple tie scores, right? So that way, we typically use an odd number for our k value, for k nearest neighbor classifier. But as we saw in the case of k being 5, we cannot avoid entirely those tie scores, right? So even if k is set as 3 or 5, we will have those some wide regions, although it is relatively smaller than the case where we have an even number. And also another point that I want to make is, so you guys know the overfitting and underfitting stuff, right? And let's see. Overfitting means we almost perfectly fit our training data, but not much on the test data, right? And then underfitting is the case where we didn't even properly fit the given training data, right? And so what about the bias variance? So overfitting corresponds to high bias or low bias. I mean, if one is high and then the other will be low, right? But anyways, so this one is first and this one is second. So let's just do the poll. The first one, high bias corresponds to overfitting, or low bias. Okay, so overfitting means it has a low bias. Okay, so you can think of this bias as the degree of fitting your training data, right? That you know the label about, right? So training data, the label is known, right? And then the degree of how much you fitted your training data using your model, that is corresponding to the bias. But there is a kind of a sweet spot when, in terms of degree of how much you fit your training data using your model. So if it is too much, and then although you had a really so maybe if I explained in an opposite way, sorry about that. But if you if you fit your model very well, I mean, if you fit your training data very well, and then it corresponds to low bias, right? Low bias, which means the low bias means you fit your data or training data very well, right? But if it's too much, and then it actually turns into a bad thing, and then that's when this variance term start to increase. Okay. So if you fit your data overly or too much, and then even though you have you achieved a zero bias, but you're starting to get higher variance. Okay, so both of them are not good. Okay, so both of neither of them are not good one. So we have to minimize both of them. But if you minimize bias too much, and then you will get high variance as well. And so overfitting and underfitting. So we have two cases. And then what is the case corresponding to K being high or K being low? For example, K being 10 or K being 1. Is it like this or is it like this? So this one, and then the cross one being the first one, the second one. Okay, so first one got more votes. First one got the more votes, right? So we have to figure, so the task is to figure out, determine low K is bringing overfitting or high K value is bringing the overfitting, right? So let's see. It doesn't have K values. Let's see. Nice. Okay, let's look at this. It doesn't have K values either. But yeah. So which one do you think is the lowest K value? The left, upper left one, or the right bottom one? I mean, which one has the lowest K value? Upper left, right? Upper left, right? And then if we have larger K values, I mean, like the region around the decision boundaries, right? So the behaviors will become different depending on different K values, right? So this is corresponding to the K being the lowest as 1, for example. And then if we have large K values, and then we have kind of an effect of an averaging out, right? Averaging out. So for whatever regions or whatever positions, if we consider a large number of nearest neighbors and their majority voting, and then we will roughly get the consistent kind of predictions, right? So it doesn't really change much on our decision boundaries, right? So in that case, it is corresponding to kind of an underfitting, like a simpler model, right? And then this one is like an overfitting case. So for example, in this case, so in the case of K nearest neighbor classifier, we can even think, we can also still think about the training accuracy. Okay, training accuracy. So yeah, in the K nearest neighbor classifier, there is no really separation between the training phase and the testing phase. So in this case, including myself as a candidate for the neighborhood, if we use K as 1 as a K nearest neighbor classifier, and then the nearest neighbor will be always myself, right? And then the result of the classification will be always the same as the label of myself, right? But if we consider the neighborhood, then even if I am a positive classes, but if 2 of my other neighbors are all negative classes, and then when doing the majority voting, and then I will be classified as a negative one, which is a which is obviously different prediction result from the known training data, known training data of myself, right? So that way, if K is larger and larger, and then I will get influenced more and more by my neighbors, which may have different labels from mine, and so we cannot fit our data properly. Okay. Okay, so that was about the K nearest neighbor classifier. So yeah, this CS231N discusses about the regularization in terms of an L1, L2, and their combinations, which is called the what? What's the name of the regularizer that combines both L1 and L2? So I should have yeah, I should have included it in our quiz, but what was the name of it? What's the name of it? Huh? What's that? Yeah, elastic net, right?
Excuse me. Are you answering the questions? Are you answering the questions?
Kind of.
Can you translate it for us?
Oh, I see. Oh, I see. Yeah. Okay. Yeah. Yeah, I'm looking at this second one. So that is. I didn't expect to translate it into English, but it's saying L2 regularization. Yeah, the lecturer said that L2 regularization is diminishing all the weights of our parameters kind of equally, right? So yeah, the question is how do we understand that mathematically? Okay. Okay, so yeah, where is elastic net? What's the page number? Can anyone give a page number? 34요? 지나갔나 보네. 여기? 아, 렉처 3에 나와요, 이거? 아. Okay, so if we use a L2, L1 and L2 regularization, and then it is called the elastic net. Okay, and then let me just explain a little bit of the effect of the regularization, which suppresses your parameters of your model. So if you have, for example, AX plus B, and then suppose we have a training data as maybe X1, yeah, the first training data is maybe 1, and its label as maybe 3, for example. And then suppose the current A and B. So we typically randomly initialize those two parameters, right? As maybe 2 and maybe 2. Okay. And then what is our training loss in terms of least squares, or yeah, this kind of squared loss. And then AX plus B minus Y squared. So that is our loss function. Yeah, when it comes to just considering just a single data, right? So in this case, let's just yeah, plug this into here, and then A times 1 plus B minus 3 squared, right? So this is our loss function, right? And then, yeah, I assume that you guys are kind of familiar with the gradient descent. So I'm trying to show how the gradient descent works in this really simple example. Okay, so so this is our loss function, and then we have to come up with the derivative with respect to A and B, right? So in this case, so let's just apply the chain rule, and then it's like A plus B into 3, and then yeah, let me just change A as 2, okay, to make this example more interesting. Okay, and then let's see. So in this case, what will be this number? I mean, we are computing the partial derivative with respect to A. What's the number? 2, right? So it's like we apply the chain rule. So that being the big variable, and then it's like x squared, and then if it is we compute the derivative, and then we will have this, and then we go inside of this x, right, large X, and then we look for our variable, this variable, and then the derivative will be 2, right, and so that value will be further multiplied, right. So this is how this chain rule works, right. So this chain rule is really, really important, by the way, in order to understand properly the backpropagation which is really the key kind of idea to optimize whatever types of neural networks or deep neural network models. Okay, but anyways, so this is the function of this partial derivative, and then from here the current a value is 2, right? So let's plug this guy over here, and then we also need a b as well, right? In order to compute this partial derivative with respect to a, right? So even though we compute the partial derivative with respect to a single variable a, right? But still, the function of this partial derivative may involve all the variables that you have. So that way we have an a and b. Even though b is considered as a constant, but still b can survive in the form of our gradient function, right? Okay, so let's just plug that in, then it's the 12, right? So this is the gradient with respect to a, right? So how do we update the value of an a? So a is currently 2, and then we just use the negative sign. That's why we call the gradient descent instead of gradient ascent, right? Because we want to minimize or lower our objective function, right? Okay, so if we so we need step size, and then let's just set the step size as 0.1, which is our hyperparameter, right? So it should be set in advance. And why do we use that value? There is no reason. I mean, we have to optimize that value as well by using our validation set, such as like cross validation and things like that, right? But anyways, let's just suppose we currently use the step size as 0.1, and then like this, right? And then the value will be 0.8, right? So this is our newly updated a value, right? So this is just showing just one simple example of gradient descent of a particular variable that we have. So we can do the same thing on the b by just computing the partial derivative with respect to b, right? Okay, so far so good, right? Okay, and then let's consider the situation where we have a regularization over here, and then the regularization is put over here, right? And then in the case of an L2 regularization, it is like this, a squared and b squared, and then maybe some hyperparameter. And then let's say our hyperparameter as 1/2, okay? Okay, so in this case, what would be the new partial derivative with respect to a for this newly defined objective function? So in this case, because these two functions are added together in our objective function, so partial derivative will be still the sum of the two partial derivatives, right? And so the first one will still remain the same, and then what about the second one? So what's the partial derivative with respect to a over here? So it is like 2a, right? 2a. So we currently have an a as 2, and then this was the gradient that was produced by just trying to minimize our loss function to fit our data, right? Fit our data. But to minimize this part, which is our regularizer or regularization part, and then we additionally get this amount of a gradient, right? And then a is currently 2, right? And then what is the gradient? It is 2, right? Currently, right? So yeah, let's just use a little bit smaller regularization. Okay, I think it's too much, but anyways, yeah. In this case, it is like the additional gradient that we get is 0.5 by just considering this as well, right? So 2 and 0.1 and 12 and plus like this, right? So so it's like 2 was moved to 0.8, right? Yeah, due to this gradient part, right? But at the same time, we have an additional gradient part, caused by this regularization, right? And then let's think of the sign of this gradient. The sign of this gradient. So if a was 2, which is currently the positive value, and then its partial derivative will be always represented as this. So if a is positive, and then that part is also positive, right? So it will have the same sign. So a is currently positive value, and then its the gradient value for this regularization term will also have the same sign, right? Positive, and then gradient will also be positive for the regularization part. So positive and also positive, and then we always subtract, right, this gradient from the original value, right? So that means if we have a positive value, and then positive gradient is subtracted from the original value, and then that gradient will be always produced so that your value is moving towards 0, right? So let's think of the opposite case where we have maybe a as maybe -3. So that is current parameter value, and then this gradient value will be also having the same sign, the negative value, and then we subtract the negative value, and then we actually add some positive value as well. So in that case, yeah, we have we also move this current value towards the 0. Okay. So like graphically or pictorially, we think of this kind of a one-dimensional number axis. 수직선이 영어로 뭐죠? 네? 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 버티컬? 버티컬? 이 수직 이거? 그거 말고 이 수로 이루어진 직선. Number line. Okay, number line. Okay, yeah. Okay, so let's think of 2 being the current value, and then what is the force or the gradient due to our L2 regularizer? It's like this much, right? So that is coming from like one. Yeah, this is really the hyperparameter that we set, right? Assigned to the L2 regularizer. But this part is really the important part, which is the form of the derivative of this regularizer, right? And so it is basically proportional to a, the current value a, and then the direction will always towards the 0, right? So if your current value is here, and then you will have this force, which is your gradient, and then suppose you currently have here, and then you will have a bigger force, right? But still the direction will be towards the 0. But what if we have the current value over here, and then proportional to this length or this absolute value, the magnifier, the magnitude of that gradient will be proportional to the current value a, but still the direction will be towards the 0, right? So that way your regularizer will always move, will always give an additional force to move your current value towards the 0. Okay? So that way we are kind of suppressing all the parameters. Right? But in this case, let's think about the L1 regularizer. Okay, L1 regularizer. So in this case, our L1 regularizer will be replaced as this. Right? So this is a definition of an L1 regularizer, right? And then let's think of the force, which is really the gradient value. So because we consider just a gradient with respect to only one variable, so let's just ignore this part and then consider this something like this. Okay. So in this case, what is the gradient? So geometrically, so it's like this, right? And so, although the derivative is not defined at the exact point of 0, but all the other points the gradients are defined with no problem, and then the gradient values will all be the same as what? 1 or -1, because that is like a slope of a tangent line, right? And that tangent line is the same as the original line, right? And also it's like mathematically or a little bit of a mechanically, like this function is like x and minus x if x is greater than equal, like this, right? So if your x is currently like a positive value, and then what is the derivative of it? It's 1. What is the derivative? -1, right? Okay, and then let's just consider this in the context of optimizing your variables through this gradient descent. And then your current value is over here, 2, right? So in this case, we will have this force, but what if we our value is 3, and then what is the force and the direction of that gradient due to this L1 regularizer? It is really the same as this guy, right? Because it is no longer be proportional to the current A value, right? Right? 네.
한국말로 질문드려도
네네.
그 0에 가깝게 한다는 게
네.
에러, 그러니까 로스를 0에 가깝게 하는 게 아니라 A나 B를 0에 가깝게
네.
하는 거잖아요.
네.
그걸 0에 가깝게 하는 게 좀 더 노멀한 그 경계가 나온다고 하는 걸 어떻게 알고 있는 거예요?
노멀한 경계요?
레귤러리제이션을 하는 이유가
네.
좀 더 노멀한 경우를 찾으려고 하는 거.
노멀하다는 게 어떤 뜻이에요? 좀 부드럽다? 네.
되게 오버핏돼 있는 경우를
네.
찾지 않고
네.
그것보다 좀 덜한 경우, 표현 어떻게 해야 될지 잘
네네네.
모르겠어요. 그런 거라고 알고 있는데.
네네네. 그러니까 이게 so let's just think of like this kind of case, AX2 and maybe BX. Yeah, it's like example that we considered. X2 and CX1 squared and DX2 squared and E equals 0. So you guys understand that? Yeah, we understand this one can represent all the various complicated decision boundaries, right? So in this case, those A, B, C, and C, D, and E's are our learned parameters. But if they are close to 0, and then their kind of curvature is not really like dramatic. So for example, like 1 and 2, maybe 1,000, and maybe 500, and so on. And then in that case, it is really like showing complicated decision boundaries. Although I'm not showing the actual examples, but yeah, potentially or generally, if we allow our parameters to have really large magnitude, and then altogether their linear combination this kind of overall formulation or overall equation may become really complicated decision boundaries. But if they are all close to 0, and then they are like a little bit smooth and the curves that doesn't have really dramatic changes.
비슷한 맥락에서 사실 전부 다 0에 가까워질 필요는 없을 것 같은데
네.
예를 들면 이 같은 경우에는 0이 아니더라도 드라마틱하지 않을 수 있는 그런 경우가 꼭 전부 다 0으로 해야 되나라는 의문이 들어요.
Yeah. Right. So he's asking about the potential way of assigning different amount of forces for different variables. So for example, in this particular case of a regularization, they will get all the, fair, not equal amount, but we treat them fairly, right? So if A was 2, and then that corresponding force will be the same as the force that B will get when B is 2, right? So if A and B are currently the same value, and then they will get the same force, right? But what if our situation may require some some subset of our variables to have a less force than the other, right? Or some other variables may have a higher force, right? So in that case, usually when imposing the regularization of an L1 and L2 regularization, we do not know which variable to put more forces in terms of a regularization in advance, right? So we just give the same amount of force, and then we let our model to find the optimal solution based on that. And also, in terms of the amount of forces, I wanted to emphasize or point out this kind of thing. So as we saw in here, so in the case of an L2 regularization, yeah, the forces, the amount of forces will be proportional to the current absolute value or magnitude of the current parameter, right? So if it is really away from the zero, and then you will get really strong force, right? So it is really the same as like a spring thing, right? F equals kx. You guys remember that? F equals kx. Yeah. So that is really the same thing. But anyways, so that's the property of an L2 regularization. But in the case of an L1 regularization, regardless of any positions, even though the direction may change. So if it is a left side of the zero, which means currently it's a negative value, and then the direction of the forces will always towards zero, right? If it is positive, and then it will be produced it will produce the force towards the zero. So that is the common aspect or common thing or properties, but the amount of force will be different. So suppose currently we have our parameter value over here, and then over here, and then the force due to our L1 regularization will be the same, right? Because that is just represented as the constant, right? So let's think of the two variables, A and B, and A is currently 2 and B is currently 5, for example. So in this case, the regularization will really push this guy towards 0 with a large amount of force, and then this guy will have small force, right? But in the case of a L1 regularization, this force will be the same, will be the same, and so in that case, I mean, you guys probably have heard that L1 regularization will often give you sparse solution, right? Sparse solution. Sparse solution means some of your parameters in your model, even though maybe you used this 5 parameters as your optimization variables, and while doing the optimization, some of them will eventually become 0, right? So maybe 3 of them are 0, which has the effect of not using these variables at all from the beginning, right? So that is a final solution, and that is called the sparse solution. Okay, you guys know what the sparse solution is, right? So some of them are exactly 0, right? Like 3 of them are 0. So that is called the sparse solution, because only 2 of them are non-zero. So non-zero values are sparsely found. So that's the meaning of the sparse solution. So in this case, so if we exert the same amount of force, regardless of their distance from the origin or 0, and then eventually some parameters will become easily just a 0, because we just put the same amount of force. But in the case of L2 regularization, even though this guy will have really large force, but suppose your variable is maybe A value is a 0.001. So in that case, in proportional to that value, the forces will also be really minimal or very, very small, right? So in that case, you will almost have no forces, and thus it will just remain as that value instead of just becoming exactly 0. So that's the reason of getting the sparse solution in the case of an L1 regularizer. So some student had a question around here. Is there any questions?
About the project? What kind of subject you got?
It's just free topics that you choose.
Anything related to vision or maybe also natural language processing?
Yeah, and even speech, and maybe other time series data or any kind of data. Yeah, as long as you use neural net and deep learning and so on. And it doesn't even need to be really deep. So as we will study, probably that will be, I'm not sure, but that will be part of your self-study kind of, that watches the video lectures as well. But I plan to cover some of the word embedding stuff, and something called the word embedding is just literally using the 2-layer neural net or just one hidden layer neural net. So In that case, we cannot really call it as a deep neural network, but that's really the popular techniques used together with all the complicated deep learning models. So that's quite important. Any other questions? Okay, so I believe this question about the L2 regularization was covered, right? If not, please, explain again your questions. Okay, so regularization for so what if the hyperparameter assigned to the regularization term is the negative? So we don't consider that. Okay, so again, loss is always positive or greater than or equal to 0, right? And so in case your loss is composed of multiple different terms. So in the previous examples, we have the term corresponding to the data fitting, and then the other term corresponding to the regularizer, right? And then each of these terms should be non-negative, and they should be combined by using the positive hyperparameter, positive ways. Okay. So at least as far as my knowledge goes, I haven't seen any kind of cases where we use negative kind of thing. Okay. Although some terms may be kind of a negative value. So so it will be covered. It might have been covered or will be covered in some of our video lectures of this CS231N. But what if you want to maximize some measure? Maximize some measure. So you want to maximize something, but we always represent it as a minimization of our objective function. So in that case, we just put the negative sign of the term that we want to maximize, and then and then we can minimize that. That is equivalent to just trivially equivalent to minimizing maximizing something is equivalent to minimizing the negative of that something. Okay, so usually this is not considered. So you can just safely ignore this case. Okay. So in the hinge loss, okay, so it's, there's a hinge loss. Okay, so the reason why the margin in the hinge loss doesn't matter is, let's see. So this is called our margin, right? 1. And in the case of support vector machine, we just use the margin always as 1. And that's because that margin value, I mean, as long as that value is just a fixed value applied to each of our data items, for different sets of these prediction scores, I mean, if as long as we use just a fixed margin value, and then the actual value of that margin, I mean, that fixed or common margin value doesn't matter, because as we saw in this somewhere here, so in this case, what is the hinge loss in this case? So how do we compute the hinge loss? So for this given image, and then these 3 are the class prediction score, right? And then there will be the score corresponding to the ground truth class. And then here, this one has the ground truth class as a car, right? And this is the score that we want to focus on, right? And then we compare this guy with all the other classes, which are sometimes called the negative class. Okay. So for this image, this is a positive class because that is really the class of that class. And then these are not true one. So that is sometimes called the negative class. So for the single positive class, and then we compare, we compute the score differences between this a single positive score with each of our negative class scores, prediction scores, and then compute the difference. And then if that difference is always greater than or equal to 1, I mean if this one is greater than each of these values by the amount of 1, which is called margin, right? And then that's when we have zero loss, right? So we are perfectly happy. Okay, but suppose we have the difference as 0.5, for example. I mean, yeah, so in this case, 4.4. So in this case, we didn't satisfy the margin yet, right? So in that case, the loss is what? 0.5, right? 0.5. 네? 그러니까 요 두 개는 로스는 0.5죠? Yeah, okay. So in that case, yeah, it didn't clearly satisfy the margin that we set as 1, right? And yeah, the trivial and the easiest way to increase this margin is just by scaling up our linear combination coefficient, right? Linear combination coefficient. So somewhere around here, yeah, it mentioned about like just multiplying the optimal coefficient or weight parameter W by 2, and then all the differences among these resulting values will become twice. I mean twice, right? So suppose we have a particular W that produced all these scores, and then suppose we now use 2 times W as our parameters, and then all these scores will be doubled, and then this margin of 0.5 will now become 1, right? So that way, so that particular value of setting the margin as 1, I mean the value of 1 doesn't really matter.
But what you said it was if you multiply 2 times, right, then the loss remains the same. Is that what you're saying?
No. So yeah. Although it's a quite special case, but let's just consider like a perfect case where we have all zero loss. Okay. So so in this case, this value is greater than each of these two values by the amount of at least maybe 0.5. Okay. So if we were set the margin as 0.5, and then let's suppose the current situation has zero loss. Okay, so that means at least our positive class score is greater than all the negative scores by the amount of 0.5. Okay, so in that situation, the loss will not be zero, right? If we just consider our margin as 1, right? Does it make sense? But in that case, we can just we have just a really simple way to make that situation to become, to have the zero loss. And how? We can just simply multiply W by 2 and then use it as our parameter, and then all the differences will become 1s, and thus the loss will suddenly be 0. Does it make sense? 이해 가죠? 설명 다시 해줘요, 혹시? 한글로? 라도? 됐죠? Okay. So that, yeah, due to kind of this intuition, based on this intuition, in both, in SVMs, the margin value itself doesn't matter. So we just set it as some constant value. And yeah. Any other questions so far?
In the video, you mentioned that K4 validation is very useful for smaller data sets. Right?
Which validation?
K4.
K4, okay, yeah.
They say it's very useful for smaller data sets.
Uh-huh.
Can you explain why?
So let me say this. So when doing really like a serious task by using a deep learning, For example, you want to train your own model by using ImageNet data, which has maybe 1 million data items or images, and then you cannot do the cross validation. In that case, we typically use just a fixed setting. So where we have maybe 100 data items, and then we just split them into maybe 8 to 1 to 1, and then this is your fixed training data and validation and test data. So we just fix that setting, and then training and do the training and testing only once by using that setting. But in the case of a cross validation, it's like they are rotating with each other, right? So some parts are becoming training data or training part, and then sometimes it will work as a validation or the test data, right? So in that case, the main advantage of using cross validation is that you can so in this case, what is the number of data item over here? It is only 10, right? So our conclusion or our kind of evaluation or final score about how good our model is performing is only evaluated based on using like 10 number of data. Okay, 10 data is really small one, right? So can we rely on that result that was produced by using such a small number of data, right? So in that case, we may feel a little uneasy or uncomfortable, right? So in that case, the effect or benefit or advantage of the cross-validation is that so we will get the prediction score for this, which works as our test data, and then this one will work as also the test data in some other settings, right? So in that case, if we just average out those prediction scores, and then our prediction scores will be based on the on using entire data items. So that evaluation or performance measure was evaluated based on the entire full data, right? So we feel a little bit more comfortable, right? But what's the price for doing so? It's just computation, right? So if we do the 5-fold cross-validation, we have to do the training and the testing 5 times, right? But if we just fix that setting just once and then compute the do the testing only on this set, and then it's just a one-time process, right? So cross-validation is literally taking the k times more computation than the fixed setting, right? So if our data has really many data items, and then we cannot do the cross-validation because it will take maybe a year, right? So only one kind of setting, it will take maybe, suppose it takes a few weeks, right? And then if we do the 10 cross-validation, a few weeks will be tens of weeks, right? So practically, it will be quite taking a long time. Okay, so that's why, that's how this small data is related to the cross-validation. But in practice, if we have really sufficient number of data, and then we don't do the cross-validation. Any other questions? Okay, so have you guys understand this figure? So what's the y-axis? So I want to really improve this figure, but this one is loss, right? And then, so this what is the x-axis? So it is SYI. Okay, what is YI? YI is the ground truth label of I's data item. Okay, so here, what is the SJ? So for let's see. Okay, so let's think of this car case, and then YI is 2 because this has the label of this second category. Although if it's a 0 based, and then it will be 1, but if it is a 1 based, then it is 1 and 2. It's the second category, right? And then this S of YI is the score, prediction score, right? So let's just make it as our variable x. Okay, let's just suppose we have a freedom to change that value, and then now But instead, let's just fix j as 1. If j is 1, and then it will correspond to this score. And then let's just consider that value as the pre-given value. So this value is 1.3. And then the real origin will be somewhere around here, right? I mean, here 0, and Sj is currently 1.3. And then our x-axis, which can have a different values, so that is corresponding to this variable. So if this guy was fixed as 1.3, and then setting this as a variable, and then if it is greater than or equal to 2.3, and then the loss becomes 0, and that is corresponding to this blue line. And then if it is starting to become less than 2.3, and then it will start to create some loss, some non-zero loss, and then that loss is like this. So it's a really simple one, but it's a little bit difficult to read. Okay, so the time's up. So I wish I had covered more, but we will continue the next time. But again, in the next week, we will have no classes. But instead, I will just assign some other additional video lectures. Okay, thank you. 네네. 감사합니다. 네.
거기서 워시도 아웃이나 편에서 그렇게 한다고 쓰는 거라고 하더라고요. 그렇게 이해를 해야
이게 그러니까 스케일 팩터 아까 그러니까 좀 전에 얘기했던 그거인 것 같거든요. 그거를 그냥 절대값으로 하면 그러니까 마진이 지금 좀 작다라고 하면 그 값 자체는 1에 비해서는 부족하지만 아까 얘기했던 것처럼 우리의 그 선형결합의 파라미터를 그냥 늘려주면 저거는 그냥 간단하게 해결이 되니까 그 값을 그냥 1로 세팅해서 쓴다 뭐 이런 의미인 것 같아요.
궁금한 게 클래스 인밸런스 할 때요. 예를 들어 그냥 나이브 베이즈 모델 같은 경우는 이게 프라이어 곱할 때 그 인밸런스 된 값이 들어가니까 사실상 좀 클래스 인밸런스 문제에 좀 취약하잖아요. 나이브 베이즈 모델은. 근데
뭐가 들어갈까요?
그러니까 나이브 베이즈 모델은 그 포스테리어 계산할 때 프라이어 값도 같이 넣어줘서 하니까 만약에 클래스가 고양이가 10이고 개가 100이면 개 쪽으로 좀 더 가깝게 되게 되잖아요. 그런데 딥러닝 모델은 명확하게 그 텀이 있는 게 아니고 바이어스 예시는 뭐 이해는 갔는데 바이어스를 빼고 그냥 클래스 인밸런스 된 웨이트 학습하면은 그것도 좀 도미넌트한 영향이 있나요?
그 바이어스 질문 한 게 강경 학생이었어요 혹시? 아니요.
바이어스 질문 하려 했는데 이미 있어 못했고.
그게 맞아요. 그러니까 그게 클래스 임밸런스를 어느 정도 우리가 직접적으로 그 프라이어를 그 클래스 개수에 비례하는 그러니까 클래스의 데이터 아이템 개수에 비례하는 프라이어로 주지는 않았지만 명시적으로 그런 식으로 지금 스코어 자체에서 그러니까 더 많이 나타난 클래스는 그 바이어스 값을 더 많이 줌으로써 얘네가 일단 다른 애들과 대결을 했을 때 뭐 예를 들면 소프트맥스에 들어가기 전에 얘는 바이어스를 더 많이 주면 얘가 더 하여튼 뭐 좀 그 템플릿 매칭이라고 해야 될까요? 여기서 나오는 그런 템플릿 매칭에서 그냥 그저 그래도 이제 바이어스가 확 클 수 있으니까 그러니까 걔가 이제 디폴트로 더 큰 값을 부여를 받게 돼요. 그래서 그게 맞아요. 여기서도 바이어스가 그런 역할을 이제 그러니까 확률적으로 프라이어로서 이렇게 그런 확률적인 프레임워크에 사는 건 아니지만 그런 역할을 분명히 하고 있는 게 되고요. 그 다음엔 그 바이어스 이펙트를 없애려면 사실 뭐 좀 그거를 얘가 학습한 그 바이어스 자체를 바이어스 텀 자체를 아예 무시를 해버리고요. 무시를 해버리고 그냥 그러니까 시그모이드 같은 경우는 어떻게 보면은 그 바이어스에 따라서 어쨌건 스트레시홀드는 0.5로 픽스가 돼 있잖아요. 바이너리 클래시피케이션을 하고 시그모이드를 하나로 뺀다고 했을 때. 그러면 그 바이어스가 커지면 이제 내적 값이 0이어도 그 바이어스만큼 확률 값을 부스트를 받잖아요.
네.
그러니까 이제 그런 거를 이제 바이어스를 그냥 없애고 그 스코어에서 그 트레시홀드 0.5가 아니라 그러니까 다른 값으로 후처리적으로 아니면 그 밸리데이션 셋을 가지고 그거를 또 옵티마이즈를 하고 그래요.
그 일반적으로 약간 모델 학습할 때
네.
그런 임밸런스한 걸 아규멘테이션 한다거나 그렇게 해서 좀 맞춰주고 트레이닝 시키나요? 아니면
아, 네, 그런 어프로치도 있어요. 그런 어프로치도 있어요. 그러니까 그게 뭐더라 까먹었는데 맞아요. 그런 게 있어요. 그래서 그러니까 큰 데이터를 없애거나 그러니까 10개, 100개면 100개에서 90개를 없애면 10개, 10개가 맞춰지는데 그럼 90개를 못 쓰잖아요. 그래서 10개를 예를 들면은 10배 더 많이 트레이닝을 하거나 이쪽에서 데이터 어그멘테이션을 그래서 이렇게 더 많이 해서 이거 뭐 리샘플하고 뭐 이런 테크닉들이 좀 있어요. 그래서 이제 밸런스를 맞춰서 이제 학습 당시에 그냥 어떤 프라이어 측면에서는 이퀄리 그러니까 웰 밸런스 된 그런 식으로 하는 경우들도 많이 있어요.
미니 배치 구성할 때 뭐 같이
네,
다른
그렇죠.
결합
네, 맞아요. 그리고 그게 어떻게 보면은 그 사실 그 리얼 및 그 겐에서도 리얼 페이크를
네.
우리는 그냥 아무 생각 없이 같은 수를 넣어주잖아요.
네.
그러니까 그게 어떻게 보면은 그 바이어스 측면에서 우리는 그러니까 그러니까 밸런스드 된 셋으로 일단 세팅을 하고 이거를 하겠다는 거라서 거기서 약간 그게 왜 그러면 똑같은 개수를 넣어야 돼? 라는 측면에서도 또 생각을 해보면 뭐 약간은 좀 적당히 한 거라고 볼 수 있을 것 같아요.
선생님 아까 그 텀 헷갈리셨다는 거 어떤 분이 파라볼라라고
아, 파라볼라 맞아요. 파라볼라. 파라볼라 가만있어. 파라볼라가 포물선이죠?
네.
네, 맞아요. 네.
네, 먼저
근데 하이퍼볼릭 뭐가 있는데? 그게 쌍곡선인데. 하이퍼볼릭 어쩌군데? 하이퍼볼릭 커브인가 그냥?
Can I ask you something?
아, sure.
I had a maybe you can. You have to leave.
Yeah, it's okay. Yeah.
Okay, I have maybe like a quick my idea for a research project, but that
Oh.
would be maybe it's too long. Maybe it's too long.
Okay.
I'll ask you later.
Okay, maybe the next time.
Yeah, yeah, sure.
Yeah. I may have to leave in about 5 minutes. So.
교수님 다음 주에 수업 월요일에 있는 거예요?
네?
다음 주 수업 월요일에만 있는 거예요?
아니요, 둘 다 없어요.
월수 다
네.
저
네.
진짜 완전 죄송한데
네.
질문 드릴 게 있는데요.
네.
제가 친구들이랑
네.
공모전을 하는데
네.
그 데이터 공모전인데 데이터가 패널 데이터예요. 근데
네.
타겟이 카테고리가 4개거든요. 그거를 저희가 생각했던 게 XG 부스트를 주차별로 돌리고
네.
LSTM으로 묶으면 어떨까 생각했는데
네.
근데 약간 별로더라고요, 성능이.
주차별로 XG 부스트를 돌리고 그 다음에 LSTM을 뭘 하신다고요?
네. 이상하죠.
주차별로. 네, 그러니까 그게 XG 부스트의 아웃풋은요.
네.
거의 그게 파이널 클래스 스코어의 형태를 가지는 아웃풋으로 뭔가 나올 거잖아요.
네, 소프트 클러스터링해서
네.
확률 값으로 나와요.
그러니까 그렇게 되면은 뭔가 이게 좀 그러니까 XG 부스트가 그러니까 그 최종 스코어를 내려고 노력하다 보니까
네.
중간에서 저희가 이렇게 좀 잘 프리저브 해야 되는 정보를 많이 잃었을 수 있거든요. 네, 그래서 이제 이미 많이 잃어버려진 정보, 그러니까 XG 부스트가 나름대로 최선을 다한다고는 하긴 했지만 어쨌건 파이널 그 클래시피케이션 스코어의
네,
형태로 뭔가 뽑아준
나와서,
거잖아요.
네, 네.
그러니까 그거를 만드느라고 뭐 최선을 다하긴 했으나 이 중간에 뭔가 뉴럴넷이 좀 그러니까 얘가 좀 얘가 생각할 때 자의적으로 버린 거를 뉴럴넷에서 더 이상 볼 수가 없는 거잖아요.
네.
네, 그런 측면에서 좀 약간은 좀
문제가
개선의 여지가
있죠.
있지 않을까 좀 썩 괜찮아 보이진 않네요.
그쵸.
네.
괜찮지 않더라고요.
오히려 순서를 바꾸는 게 차라리 뭐 나을 수 있거나.
그럼.
근데 이게 또 이게 뭐 연결하면 이게 하여튼 전체적으로 백프랍에 의해서 학습이 되려면 이제 뭐 XG 부스트 그러니까 LSTM 먼저 XG 부스트 나중에 이렇게 하면
그래서 저희가 생각한 게 아예 그냥 딥러닝 쓰지 말고
네.
로지스틱을 쓰자 생각을 했는데
네.
패널 데이터라서 멀티노미얼 로지스틱을 쓰는 게 힘들더라고요.
시퀀스 데이터라서요?
네. 근데 그게
시리즈랑?
가능한 건가요?
네. 네.
가능하긴
네.
하던데.
네. 네.
아, 네.
네. 그러니까 적당히 시간 정보를 어느 정도 버리고 뭔가 네. 그냥 언제 시간에 나타났든 상관없이 그냥 뭔가 구성을 하시거나요.
네.
그게 물론 이제 시퀀스 정보를 잃어버리는 거긴 한데
네. 그럼
뭐 그래도 성능이 뭐 그래도 그거 한번 해봄직하고요. 그렇게까지 나쁘진 않을 수 있고요. 그 다음엔 그 시퀀스 자체를 처리하지 않고 좀 부분적으로나마 이제 시퀀스를 처리할 수 있는 건 이제 n그램으로 이렇게
네.
N그램이라고 이제 그 네, 뭐 전체 시퀀스가 뭐 10이다 그러면 저희가 이제 3짜리의 시퀀스들을 뽑아서
네.
그걸로 저희의 뭔가 저 백오버즈 같은 사전을 좀 구축하면 네, 뭐
네.
그러면 이제 부분적인 시퀀스들 그리고 그들이 이제 그들 간에 나타난 그 시퀀스 정보는 무너졌지만 그 세계 내에서의 시퀀스를 저희가 잡아낼 수가 있어서
네. 알겠습니다.
그리고 비디오 지금 촬영해 주시는
아,
분이시죠?
네네네.
아,
저도 원래 원래 제가 앞으로 나눌 거예요. 저 그냥 땜빵으로.
네, 알겠습니다. 감사합니다.